Good morning, everybody. So it is a great pleasure for me to introduce Professor Succi. I am Luca Helte, Professor of Numerical Analysis at CISA, International School for Advanced Studies. And today, I would like to introduce to you one of the fathers of one of the most successful methods in computational physics and in numerical analysis of the last century. And the method is the lattice-Boltzmann method. And Professor Succi's book of 2001 in lattice-Boltzmann method achieved the astonishing number of more than 60,000 citations up to date. So that means that he has an enormous amount of researchers and an enormous amount of students and scholars that rely on his results in order to proceed with their research in their career. Professor Succi originally is from the University of Bologna, from the academic point of view. He studied nuclear engineering, if I recall correctly, and then he received his PhD in plasma physics from the École Polytechnique Fédérale de Lausanne. Currently, is both the University of Harvard and the Italian Institute of Technology, and previously he was at the IAC CNR in Rome. He's been a fellow of the most important universities all over the world. So everybody wants to have him visiting, and everyone wants to have him as a fellow. So just to name a few, Freiburg Institute for Advanced Studies, the Schrödinger International Institute for Mathematical Physics, Yale University, Harvard University, and many others. The list of prizes that Professor Succi achieved and received is very long, so I'll just mention a few of them, the most important ones. So he received the Humboldt Prize for Physics, the Killam Prize from the University of Calgary, the Raman Prize, the Raman Chair from the Indian Academy of Science, and the Sigillum Magnum from the University of Bologna, from the alma mater, and the Burney Other Prize from Second Computational Physics. And last but not least, he is a recipient of one of the most prestigious funds that one can achieve in Europe, European Research Council grant, for his research on full-scale computational design of porous mesoscale materials. Last but not least, I believe Professor Succi is an incredible speaker. He's been one of the we've had the honor to host one of his courses in the Master in High Performance Computing that CISA held jointly with the ICTP a couple of years ago. And this course was one of the most successful courses, and the students really appreciate it. So it is with great honor, and it is a great pleasure for me to leave the stage to Professor Succi, and I'm really looking forward to your presentation that is, I'm sure will be astonishing as all the other presentations I've seen from him. Thank you very much.
Hello, good morning. Too strong. Good morning, everyone. Thank you, Luca. I'm kind of blushing for this very nice introduction. And I would like to thank the organizers. It's always a great pleasure for me to be in Trieste, a city which I really love, and also among friends at CISA and ICTP. Luca mentioned lattice-Boltzmann, which kept me busy for basically my entire life. And my wife reproaches me that I keep working on Boltzmann since before I met her. But as a matter of fact, today I took another route because I thought there is an argument, a topic which I think is of general interest for the general public. And the title is Big Data Meets Big Theory, the dawn of a new scientific paradigm. Namely, I would like to share a few thoughts with you regarding the possibility, which I think is very real, that a judicious combination of big data and big theory, I'll tell you in a moment what I mean by big theory, will give rise to a new paradigm for science, and such paradigm actually should enable us to tackle problems of complexity, which is kind of unprecedented. I wouldn't want to say that we can solve the problem that Professor Mantovani showed us, but I think we can make really transformative progress if we combine the two judiciously. Now, the very first point I'd like to make is that if you want to achieve this new paradigm, the first thing you have to do, I'm a little bit polemic here, you have to get rid of what I call bombastic big data. What is bombastic big data? We agree that we live under a data deluge, right? I think the data rain is of the order of a few exabytes a second. You know that an exabyte means a billion bytes every day rains on our head. And what do we do with this enormous amount of data? Some people, and we are actually exponentially growing, soon to reach the something 200 zettabytes. Zettabyte is 10 power 21, 1,000 billions of billions bytes. So it's an enormous amount of data. And what do we do about it? Well, some people think that we can solve any problem, I would say including the immunology problem we have been hearing from the previous speaker. And you can read it through, and they are pretty bombastic, right? The first sentence is by now famous. If you have enough data, numbers will speak on their own, and basically you don't need theory anymore because you can extract any knowledge from the data, provided you have smart navigation algorithm, which is exactly what Google, Amazon, and Facebook, etc. do. And look at this, and I don't know, do I have a laser to point? No. And, there is a sentence which I find particularly disturbing by Pedro Domingo, who, by the way, is very credited. He knows what he's talking about. He's a very credited computer scientist. He says that the master algorithm will extract any knowledge from the data before you even ask. And frankly speaking, I don't know about you, but my reaction is, the day this happens, I want to be in another planet because I like to ask for services, right? Not being given services without asking. So there is a whole list of such statements. But once you discard, in fact, the bombastic aspect, which, by the way, have a social impact, in my opinion, because these kind of statements can be, they are eye-catching, they can affect the decision makers. In a moment, I will explain what I mean. Let's take the question seriously, forget about the bombastics, and the serious question is it really true that by the time we know how to predict and act, that's all we are asking for? Take, for instance, the case of medicine. I'm not a doctor, of course, a medical doctor. But when you address your doctor, what you ask to your doctor is just the right drug that solves your problem. You are not asking him for a theory of how the disease developed, right? So, in a sense, it is conceivable that instead of having the usual change, data, information, knowledge, and wisdom, wisdom means make the right decision, you would just shortcut and say data, know-how, okay? This, I think, is a serious question that we should ask. Is it maybe that we are facing in the future problems whose complexity is such that we have to give up the scientific method as we know it from Galileo? I think this is a very deep and serious question. So the question is big data the new Archimedes lever? Is it the graveyard of theory? Is it the end of insight? And I think you may guess what my answer, which might be wrong, to this question is. And before I move to the next slide, I would like, nevertheless, to highlight a little danger which goes with the fact of trading knowledge for know-how, that then you give up generality. If you just go from data to know-how, each time your data change, you have to solve a new problem from scratch. Whereas we know from the scientific method that once we understand the phenomenon, say Newton's law of gravitation applies to apples and the moon, which is a big asset. And you should think twice before you give it up. So, sorry. I should go back, sorry. Okay, so when I read these sentences, frankly speaking, I got a little bit disturbed, so I said to myself, okay, let's take a look. Is it really true that we can give up theory? And I promise, I'm trained in studying computer simulation of complex systems, typically physics and physics interface to biology. And I promise the moment you take a little bit of time to analyze this bombastic statement, it doesn't take long to figure out they are really very shaky, very thin. There is a paper you may want to read if you're interested, and of course I have no time to go through the lists. I'll pick up just number 1 and number 4 if I have time. And Luca, you watch my time, right? So the first thing, which is basically, it's very well known, but is the kind of thing which are really never told, at least not in the bombastic big data. And the first thing is that the non-Gaussian statistic. So we are all familiar with the Gaussian law. The molecules in this room obey these statistics, a bell-shaped curve. And we all know from elementary statistics that the uncertainty, I don't think I have a pointer, right? Okay, so we let our imagination work. So we know we have a mean, which is the average of the distribution, and we have an uncertainty, which is the width of the distribution. And we know, by the law of large numbers, that if we increase the data, capital N, and we make it big, uncertainty will recede. Uncertainty will disappear, and we even know how fast. It will disappear with the square root of the amount of data, which means, in actual practice, that if you want to reduce your uncertainty by a factor of 10, all you need is to have 100 times more data. And since we are living in the data deluge, a factor 100 is peanuts. This is the triumph of big data. Enough data, any problem will be solved because uncertainty will be killed. And why is it that uncertainty is receding so fast, so to say, with data? The reason is deep. The reason is that in Gaussian distribution, there is no room for outliers. Outliers means that if I'm a runner and I am an average runner, every second people runs faster than me, 50%. If I'm a little bit better than that, I am a 1 sigma, there are only 16 people running faster than me, so I feel good. Until you realize that if you live in a city with a small city, 100,000, that means that you have 16,000 people faster than you, and then you are not so proud anymore. But if you keep playing this game and move on to 5 sigma, which incidentally I call the X line, because 5 sigma is the borderline between accident and discovery. That's how at CERN they declared that the Higgs is a particle and is not an accident, because there is less than 1 chance in a million that this is a mistake. And you can move even further. You can go to 6 sigma, just add 1 sigma, and you are the champion of the world. What I call at 6 sigma, you have Michael Jordan, which is basically the best in the world, order of magnitude 1 in a billion. So the message is that as you move further and further in sigma, just going from 5 to 6 makes you 1,000 times more special. There is no room for outliers in the Gaussian world. And the outliers are the carriers of uncertainty, and that's why uncertainty goes to 0 with the inverse square root of data, and that's why big data can triumph on Gaussian world. But big data is supposed to solve complex problems. And I promise, when you move to complex problems, could be turbulence, these would be the vortices when you drive your car under very ordinary conditions, or you go to finance, or you go to pandemics. Any complex problem in science and society today will not live in Gauss land. And this will be a talk on its own. The statistics is very different. It's so-called power law. The decay, instead of being exponential, is a power law. And as you can see, the blue and the red is Gauss and blue is power. If you are close to the average, you cannot tell them apart. But as you move further away, sigma to sigma, blah, 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 it's a completely different world. The outliers are much more numerous, and so a complex system supports uncertainty, supports diversity and uncertainty. And formally, sigma, if you do the math, is formally infinite, which means that you can forget about 1 over square root of n, and many phenomena, most complex phenomena, P is the exponent of the power law. If P is 1, there is no way you can kill uncertainty, no matter how big your data are. It's a divergent law. And if P is 1.1, if you want to reduce, I did it only once, so I might be wrong, but not much, is the exponent, P is 1.1, if you want to reduce uncertainty by 10%, sorry, by factor 10, you need 10 billions more data. And then maybe even the zeta byte might not be enough. So I'm not saying that big data is not important. It is absolutely crucial. All I'm saying is that you have to slow down, be humble, just to borrow again from the previous speaker, and acknowledge that big data is not a panacea. It's an additional dimension of scientific research, and there are problems, as there are always problems when you do serious work, okay? Incidentally, just out of, it's something which amazes me, if our 8, which follows Gaussian laws, would follow the Lorentz with P equal 2, you would see every 100 people, there would be one which is 3 meters tall. So in this room, there would probably be one person 1 meter tall, and over the entire planet, there would be people which would be 3 kilometers tall. Just to tell you what the difference is between Gauss and power laws, right? So, second point, so the message is, don't be fooled. When they tell you with enough data we will solve any problem, you should ask how much is enough data, okay? That's all I'm saying. The second point is very, very known, I mean, nothing new. You know that correlation doesn't mean causation. The fact that two variables are correlated doesn't mean that they are causally related. And there is a very hilarious database, I like particularly this by Nicolas Cage, which is very correlated with the people who kill themselves by drowning in a pool. So unless you feel that Nicolas Cage is so bad that when you watch a movie you want to kill yourself, which I don't think is the case, this is an accident. Okay. This is serious. This result is not very well known. There is a paper, it's basically a theorem by Caludo and Longo, which tells you that as you increase the size of the data, big and big and big, the Nicolas Cage correlation, which are false correlation, are exponentially growing, which means that digging out the good ones becomes an exponentially hard problem. Again, you don't find any mention of this unless you go really in the specialistic paper. So I'm back again to bombastic big data, not to big data as a scientific discipline. So these are just two, just to make the point that when you analyze this statement where the sky is blue and you are going to solve any problem, and I tell this especially to the young generation, be always critical because it's not a panacea. Having criticized, you know, I'm very outspoken because, again, I got kind of irritated by this super bombastic statement because, again, take a politician, I mean, in perfect good faith, if you are presented with the hope that you are going to solve cancer just using data, you put a lot of money. And you should not put the blame on the politician. The blame is on the scientists who make bombastic statements, okay? Having criticized big data, it's time to acknowledge that my job, which is computer simulation of physical problems, has problems. I mean, we do need accelerators. There is a complexity barrier, And we have three, there are more, but there are three major barriers, I would say, to human understanding. Number one is nonlinearity. Nonlinearity, we all know the butterfly effect. You change your initial condition, you change your system a little bit, and the system goes completely elsewhere. So you have no control, and this is a tough problem. Non-locality. You touch something here, and you have an effect far away. The pandemics has both, actually. Think of the virus. 20 years ago, you have a virus in China, reaction would be, well, you know, I'm sorry for the Chinese, but they are far away. Nowadays, we are in a hyper-connected world. Wuhan, there is a problem in Wuhan, and a few days later, the virus is knocking on our doors. And that makes the solution of this problem really hard. I mean, the complexity of this problem, when you measure in terms of number of operations you have to perform to solve the problem, it's really steep. And finally, the third enemy is ultra-dimension, which looks kind of as an abstract expression. It's very real. We live in 3 dimensions, right? We think in 3 dimensions plus time. When you want to design a drug for a new drug, and you have to decide to study how the protein moves in time, the protein lives in hundreds of thousand dimensions because you have to track actually every single atom, and there are very many in a protein. So computing the scientific method, no matter how powerful your computers, it's not enough. And I will give an example. Now I go to the positive part. CERN against COVID. It was just the breakout, I think this was March. Just by chance, I learned that CERN had set up a task force. And I asked myself, given that CERN has a lot of expertise in serious big data, because high energy physics is really a data-rich science, it was just a pure curiosity. Is it maybe the case that their expertise can be put to work for computational biomedicine, okay? Drug discovery or drug repurposing, and frankly speaking, I'm not talking COVID-19 because this is a long-term job. We don't want to see COVID again, but just in case it shows up in 10 years from now, we would like to be prepared next time, right? So this is a personal recollection. It was just announced. I mailed that to the CERN general director, and the reaction was very fast, and I'm very grateful for that. So the day after, we had a Skype meeting, and we set up a project, and I must anticipate, this is hard. I don't have results yet, and I think it will take a little while before we have. But still, I'm going to present you what I mean, as an example, of this new scientific paradigm. So there is a consortium to which IIT, my primary institution, is recently affiliated. And I also made this part of my IRC. It's called Computational Biomed, and this consortium is using the most powerful supercomputers around the world, Europe and USA, just to use the scientific method. This is what I mean by big theory, okay? And we are talking computers which are nearing the point of multiplying 1 billion floating point numbers in a second. Whoa. Well, as I said before, staggering as this is not enough to solve the most complex problems we are facing. You name it, including the pandemics. So, and I will give you I will be even more specific. This is the scope of the project. On the right-hand side, you see the spike. This is a COVID protein. And the idea would be to discover whether there are so-called cryptic pockets, which are surface cavities, where eventually you would bind a pharmaceutical, which is a small molecules on the left side. The question is, are there druggable cryptic pockets in the COVID protein? And you move, you run, you do molecular dynamics, that's the technical name, big theory. Molecular dynamics move every single atom of the protein in time. Newton's equation, scientific method, Galileo. And now I'm going to disappoint you, because the fastest supercomputer as we speak, which is located in New York City, Manhattan, Times Square, it's called David Shaw Research, they can compute 100 microseconds in a full day of a dedicated supercomputer. And in order to understand what the protein is doing, you would like to see at least the protein for a second of its lifetime. Do the math. 1 second means that you have to wait some 30 years. Now you see what I mean, that the scientific method has a problem, and other dimensions, including big data, are mostly welcome, provided they are serious. And that's exactly what we are trying to do. Just incidentally, it turns out that CERN does a similar, but it's not the same, exercise. They have their proton. The proton are just produced by the LHC. They enter the detector. And since they have a very high energy, 10 electron volts, they can give rise to many different nuclear reactions. And there is really a very, very large tree of possibilities whose probabilities are governed by the rules of quantum field theory, again, big theory. And they use Monte Carlo simulators to just track this event, and this sucks up, I think, more than 50% of their budget. So it's an heavy duty. And of course, they would like to use machine learning to release, to somehow bypass, if possible, or speed up Monte Carlo. And occasionally, this is not a general rule, but they have results in which sometimes they could, in fact, with machine learning, serious machine learning, which is a technique of big data, cut down the Monte Carlo cost by 3 or 4 orders of magnitude. Now, suppose you live in an ideal world such that these 3 or 4 orders of magnitude can be transferred from high-energy physics to quantum biomed. Of course, I'm dreaming, okay? But, I mean, dreaming is important. Then, instead of waiting 30 years, we would wait 1 day to see 1 second of protein time. So you see the potential benefit. It's not I don't think this is going to happen, but I would be pretty happy just with the square root of that, with a factor 100. So that's exactly what we are trying to do. How much time do we have? I cannot see because I forgot my glasses. Oh, okay, so we have plenty of time for the. So that means that I can be a little bit detailed. So these are 3 different protein configurations from the D. Shaw research, the fastest supercomputer. They made it available, and they have, I think, 50 different trajectories, each 100 microseconds long. What we're trying to do is kind of daring, I'm not sure it will work, is the following. This is a thick slide, but I think I have time, so I will try to go through the details. It's a cartoon because, as I said, we don't have the results yet, but this is the conceptual architecture is there. So on top, number 1, you have the molecular trajectory, which is running, and on each time step, you have the protein. So it's the full protein which is moving. And again, 100 microseconds cost you a full day. What you're trying to do, the little cycles represent cryptic pockets. In other words, you try to extract from the molecular dynamics configuration, you try to extract this feature. Is there a cryptic pocket or not? And this is a non-trivial task at all because you have a lot of data and you have to extract the relevant feature. So there is a lot of artificial intelligence in this step. But the really daring part of the project is that, I don't know whether you can see without the pointer. The red button, I don't see any red button. Anyway, it doesn't matter. I think I can work my way out. I'm almost done. Well, for this one, maybe it would be useful because this is thick. Which one? This. Is it right? Oh, sorry. I beg your pardon. I was really stupid. Okay, I'm finished. So basically, we use small stretches of the trajectories to generate digital images, because that's what machine learning is doing, is recognizing cats from dogs. You present the image, and it recognizes. But instead of cats and dogs, here we have cavities. But we cannot use, of course, the entire trajectory because we have to train the network. We give short stretches as an input to the network. This is a generative adversarial network. It's a very powerful neural network. The network is supposed to return the cryptic pockets in the long part of the trajectory, which we have available, so we can compare the network prediction with the actual simulation and iterate the loop until the network learns how to recognize the cryptic pockets in the long term. So we are asking a lot here. We are asking to predict the future, to recognize the cavities, which are not cats and dogs, is much more complicated, and to extrapolate into the future. It might not work, but it's worth trying anyway, because if it does, then we can, again, maybe save 100, factor 100, or even more. So I think I moved too much. OK. So summarizing, big theory has problems. It suffers a mounting complexity as we approach problems which are really of relevance to science and society, OK? This is a fact, OK? Big data, big D, is no panacea, OK? And certainly bombastic big D is scientifically obstructing, I would say, because it's really deceiving you. And eventually is even socially, I would say, is socially deceiving. As you see, I'm very outspoken. But big D and big T together can really work wonders and advanced knowledge much more than the two separately. So there could be really a very, very powerful synergy between the two, but it's a lot of hard work, okay? And I think this is the new scientific paradigm. This is just an example. There are others. And I think especially for the young generation, and Luca, I think in a curriculum of computational physics, no way you can forget about machine learning and big data. It has to be there. So like Professor Mantovani said, I am myself not in the generation of machine learning, unfortunately, but I'm learning nonetheless. And I like it, frankly speaking. I think it's really an additional direction, an additional dimension, and should be pursued very seriously. So these are the people involved in the, sorry. No, I'm going the wrong way. So Peter Coveney, which basically taught me, is managing the Comp Biomed Consortium. The other people, Andrea Cavalli and Walter from IIT, who are doing Walter is doing our work, and so is doing Sophia on the CERN side. And I have special thanks to Fabiola Giannotti because she picked up my email and she replied in 23 minutes, which I regard as a major achievement of my scientific career because it was really fast reply. So, and of course, I thank the organizer and thank you all for your attention.
Nice, and I wasn't expecting anything less from you, by the way. So are there any questions from the audience? Yes, please. There's a... No, I think you'll need to talk in the microphone.
Okay, sorry. Sauro, you know that simple systems can be chaotic. Simple systems can be chaotic. So what is the statement of the bombastic scientists about simple chaotic systems?
Well, I'm not sure what you mean by simple, but I think I understand what you mean by chaotic. That was one of the, I had 4 points. You just touched at one of the points I didn't cover. It's a problem, of course, because, you know, suppose I have to go from initial state to a final state, which is very complicated, and the scientific method will take a very winding and complex trajectory. A smart big data would go straight in one shot, okay? Triumph of big data, everybody's happy. Now, if I have a chaotic system, I move a little bit the initial, and the trajectory goes back on my backside. And big data is in trouble because he has learned how to go from here to here, and now he has to go from here to my back, and it's very unlikely that it will work. So I think, and it's not me, I mean, people know that if you have chaotic system, it's a challenge for the scientific method. It's maybe even more of a challenge for big data. Singularities and chaoticity, you know, there is really no free lunch. Of course, there are problems which are very well suited to big data. I mean, pattern recognition, they are doing a really good job. But the fact that, you know, that you have an algorithm which allows Netflix to increase its business, which is fair. Business is a serious thing, and it's a tough job. That doesn't mean that we can solve cancer. This is the thing which really sends me ballistic. You cannot sell a good algorithm which works for Netflix or for Facebook or for whatever. This is very welcome. They are very bright people, but that doesn't mean that you solve cancer. It's a different type of problem, and you have to analyze very seriously. So that was one of the bullets which I didn't mention. Thank you for bringing this up.
So any other questions while we wait for questions from the online people? Well, if not, I have one question myself. So in your opinion, what is the percentage of machine learning that a computational physicist or a numerical mathematician will have to use in the future years? Percentage of the ratio between machine learning and big data and big theory.
Look, I know that I don't know. But you raised it. I think your question is really the question. I think we have to somehow, and especially the young, but even us, I mean, young or people of every age, let me put it this way, we have to learn how to work in this hybrid dimension. Nobody knows what is the right mixture. It will depend on the problem, you know?
Sure.
Fact is that the young generation should know PyTorch, should know all the tools, because, I mean, they can really help a lot. So, in the end, big data is fitting in hyperdimensional space. And are you a physicist? I don't know.
No, I'm an
anyway,
electronic
for the
engineer.
physicists are very snobbish as fitting. You know the story of Fermi, that I think he was reporting the fact that with 4 parameters you can fit an elephant, and with 5 you can even fit his trunk rolling up, right? To a theoretical physicist, fitting means that you don't understand what's going on and you replace with fudge factors. I think this is too snobbish. I mean, sometimes big data can do fantastic fitting in superdimensional space, and I see quantum materials and also comp biomed, they are really doing beautiful work. I mean, there are several instances where machine learning is, Parinello is one. Mm-hmm. Yes, as usual, Michele is always 10 years ahead. He has a paper 2007 where he shows a substantial acceleration. So I think you have to be prepared to use both. And the percentage is up to you. It's an art. Science is also an art, right?
Sure. So, any other questions? If not, let me thank Sauro again for his fantastic talk.
Thank you so much.
Thank you very much.